This video contains aliens, sniffer dogs, some beeped out curse words, more aliens, really bad acting. I mean really bad. Did I mention the aliens? There is unrest in the universe. A race of evil space lizards known as the inane cult are planning to take over Earth. Their leader, Lazink Dirt, is poised for the invasion. His trusted second-in-command, Tunic Lane, boards his spacecraft and heads off with an update for his leader. Meanwhile, Horstet, a brave but exhausted savior of our world, is oblivious to Lazink Dirt's plans. He has spent many years protecting the Earth, but he is counting the days until he can pass on his mission and retire to a nice beach. His heroic protege, Days Flitch, who has been spying on the inane cult, hurries across the galaxy and arrives with an important message for us all.
Horstet, I'm so glad to see you. Days? It's so good to see you. I'm so tired of fighting this war. I don't think my body can take any more. Where have you been? I've been on a long, dangerous, heroic mission where I was very heroic. I have intercepted a transmission from Lazink Dirt, leader of the inane cult. It's not good news, I'm afraid. What is it? Let me show you.
Tunic Lane. The shape-shifting training is going well, I see.
Well, yes, it's going very well, except I can't get my hands to become humanoid. I can do the face, the body, but the hands, I can't do the hands.
Is the invasion fleet ready?
Nearly. The shape-shifting training has been successful on about half of the alien fleet. But the other half, they just can't get the hang of the shape-shifting. They can't do it.
I grow impatient for victory. Those that can't shapeshift into humanoid form shall be sent in their natural lizard form. The humans will never notice.
As you command, mighty leader.
Oh man, that is bad. Horror! How can we stop them? Well, while you've been away, we have been experimenting with training sniffer dogs to detect aliens, but we need more research. Can you get me some sniffer dogs? I found the best spaniels we have, but we only have 8 of them. That's not many. I don't know what I can do with that. I need to consult a higher intelligence. What you need is a repeated measures design. Well, the all-knowing Professor Hippo has told us that to get some kind of answers with only 8 dogs, we're going to need to use repeated measures designs. So we best get on with it. Now, repeated measures design, we can analyze again with a linear model like all the other designs that we've looked at on this module. And we're addressing a scientific question, which is whether we can use sniffer dogs to sniff out aliens. We've got a sample of sniffer dogs, a small sample, only 8 of them. We're going to need to test them. We're going to need to collect some data from them. We'll visualize that data and then we'll fit some variant of the general linear model. And in doing that, we're going to estimate parameters. We could look at confidence intervals of those parameters, and we can test hypotheses. Is it the case that sniffer dogs can differentiate humans from aliens? We're going to have to test assumptions of that model. We're going to have to test we're going to have to fit robust versions of those models if the test assumptions aren't met. Everything is the same as what we already know. The only difference is that we have a different kind of design, a repeated measures design. So let's get on and have a look at what that actually means. Okay, let's think about the simplest experimental design that we could use to test whether our sniffer dog training had worked. Now, our sniffer dogs have been through a training regime where they are rewarded when they make vocalizations when they're sniffing the thing that we want them to sniff. So essentially what we do is we put an alien in front of them. When they're sniffing that alien, if they make a little noise, we give them a little treat. So they get used to the idea that they get rewarded for making noises when they're smelling an alien smell. And then when they're smelling a human, we don't give them any treats for vocalizing. So hopefully, if the training is successful, they're able to differentiate an alien smell from a human smell. Over the course of the training, they'll be learning to make more noise when they're with an alien, because they think that if they make noise when they smell an alien smell, they're going to get a treat. So the simplest design we could use to test whether our training has been successful is to take two groups of dogs that have been through the training and randomly assign them so that some of them sniff humans and some of them sniff aliens. And we could measure how many vocalizations they make while sniffing. Now in this kind of design, this is the same sort of design that we've looked at in previous lectures. So we have different participants in different categories of the experimental condition. There's two types of variance. There's systematic variance, so there's variance in vocalizations in the outcome that is going to be created by our experimental manipulation. So in this case, it's going to be created by the fact that some dogs are sniffing humans, some dogs are sniffing aliens. So that difference should create some kind of variability in the vocalizations if the training has been successful. There'll also be unsystematic variation. We've got different dogs in the two groups, and dogs, for example, have natural differences in how much they like vocalizing. Some dogs are very chatty, as it were, and some dogs are not very chatty. So there's going to be some kind of differences between the groups, like naturally occurring differences. And there may be other factors as well, like when they're tested, maybe if the dogs are particularly hungry in one of the groups, that could be a confound or something. So there'll be some kind of other variability in vocalizations due to factors that we perhaps haven't measured. So we always have these two types of systematic and unsystematic variance. Now, when we use repeated measures design, what we're doing is we are using the same participants in all of the experimental conditions. So in this case, we've got our 8 dogs that have been trained. That's all we've trained so far. And we need to test whether they can differentiate humans from aliens. So what we could do is we could test the same 8 dogs, get them to sniff a human and measure how many vocalizations they make, and at a different point in time get them to sniff aliens, see how many vocalizations they make. The design hasn't changed. All that's changed is that we're using the same dogs in each experimental condition. Now what this should do in theory is reduce the unsystematic variance, because by using the same dogs in the two conditions, well, we know those dogs have exactly the same propensity to vocalize because it's the same dogs, so there shouldn't be any difference there. We know their noses are going to be equally as sensitive because it's the same dogs, so it's not going to be the case that the dogs sniffing the aliens have more sensitive noses than the dogs sniffing the humans, because we're using the same dogs. So across that group, they have exactly the same sensitivity in smell. Yeah, that's probably a good enough way to put it. So by using repeated measures design, hopefully we are reducing the unsystematic variance. We're controlling a lot of factors across the experimental conditions. So the benefits of repeated measures designs are, on paper, they're more sensitive. So you should reduce the unsystematic variance because a lot of things are held constant across the experimental conditions because you're using the same participants. So you should get more sensitivity to experimental effects. We should have a more sensitive design to detect whether our sniffer dogs can differentiate aliens from humans if we use the same sniffer dogs. Hooray! The other good thing is it's an economical way to test experimental hypotheses because you need less participants. So in this case, 8 participants is still really, really small, But it allows us to at least test this hypothesis. If we had to divide those 8 dogs into 2 groups, a group that sniffed humans and a group that sniffed aliens, we'd only have 4 dogs in each group. That would be an awfully small number of participants. So it's a more economical design as well, because you need fewer participants. But you do have to be aware that participants can get fatigued. So if you're subjecting participants to like hundreds and hundreds and hundreds of experimental conditions, they are going to get fatigued. The quality of their data is going to be poor. That shouldn't be a problem for us because we're only going to have a very small number of experimental conditions. Okay, so the design we have settled on, thanks to Professor Hippo's wise advice, is this. To test whether our puppies can sniff out aliens, first off, our outcome measure is self-evidently going to be vocalizations, because that's what we've been training. So we're going to let them sniff an entity for 1 minute, and we'll count the number of vocalizations they make during that minute. Now, to test the hypothesis, we are going to vary the entity that they sniff. So on one occasion, they're going to sniff an alien, not in humanoid form. On another occasion, they're going to sniff a human, which is a control for whether they can detect aliens versus humans. We're also going to let them sniff a mannequin, which is a control for them sniffing something in humanoid form that's not a human. And we're also going to get them to sniff a shape-shifting alien. So this is an alien that is able to transform itself into humanoid form. So across these 4 different entities, the dog gets to sniff each one of them for a minute, and we count the number of vocalizations. And for each dog, they'll sniff them in a different order, and that's to get rid of any potential confound of the order in which they sniff the entities. We also are going to have a variable to indicate the dog's name, and as you already know, there are 8 dogs in total. Here are the data. So we have our 8 dogs: Milton, Woofy, Ramsey, Mr. Snifficus III, Willock, the Venerable Dr. Waggy, Lord Centicle, and Professor Nose. And each score in each column represents the number of vocalizations they made while sniffing each of the 4 entities. So for example, Milton made 8 vocalizations while sniffing an alien, 7 while sniffing a human, 1 while sniffing a mannequin, and 6 while sniffing a shapeshifter. Now, a couple of things I want to note. First of all, if we look at the means for each of the entities, these are the things that our model is predicting. Essentially, these are the predicted values from the model. So we've got about 8 vocalizations when an alien was sniffed, about 4 for a human on average, about 4 for a mannequin on average, and just under 6 for a shapeshifter on average. So they're the predicted values from the model, exactly the same as in a between subject or independent design. So that's what we're testing. We're testing whether those values are different. So that represents our experimental effect. But I also want you to note that the different dogs vary in the effect that the experiments had. So for example, if we look at the Venerable Dr. Waggy, has scores of 7, 5, 6, and 7. So basically, there's kind of almost no experimental effect there. It doesn't matter what he's sniffing, he gives between 5 and 7 vocalizations. So it looks like for him, the training hasn't worked. And we can tell that because if we look at the variance in those 4 scores, so the variance across 7, 5, 6, and 7, it's pretty small, 0.92. So it looks like training hasn't had very much effect on the Venerable Dr. Waggy. Now if we take another dog like Professor Nose, who perhaps got his name because he's a very good sniffer, we can see that there is a lot of variability in the vocalizations that that dog makes across the entities. So when it's an alien, he does 12 vocalizations. When it's human, he only does 6. When it's a shapeshifter, he does 1. When it's a mannequin, he does 8. So the variance across those scores is huge in comparison to the Venerable Dr. Waggy. So for Professor Nose, it looks like he really has a lot of variability in his vocalizations depending on what he's sniffing. So the point here is there are individual differences in the effect that the experiment has had. There is variability in the extent to which the training has been successful. So for a dog like the Venerable Dr. Waggy, the training hasn't been very successful. His vocalizations are really pretty similar across the 4 entities. Whereas for, say, Professor Nose, it looks like the training might have had more effect. There's a lot more variability in the vocalizations that dog makes across the entities. So the point here is that the experimental effect is kind of embedded within the individual, and there are individual differences in the extent to which the experimental manipulation has had an effect. Okay. So this is what the data look like in R, just so that you're not confused by the previous slide. So we have it in long format. So you can see we have dog name as a column, and our first dog, Milton, takes up 4 rows, but those rows distinguish the different entities that were sniffed. So that's coded in a different column, and the final column for vocalizations shows the number of vocalizations he made for each entity. So this is known as tidy data format or long data format. This is just to illustrate that this is how the data are laid out, and we could scroll down and see some of the other dogs listed there. And you can see each dog takes up 4 rows because they sniffed 4 entities. So let's have a look how we would deal with repeated measures in a general linear model framework. Now, to keep things simple for the time being, I'm going to strip down the design and just pretend for a minute that the dog sniffed only aliens and humans. So there are just 2 kind of conditions here. They just sniffed aliens and humans. Now, we've seen from previous lectures where we looked at the general linear model that we can represent a predictor that has 2 categories with a dummy variable coded with 1 for one category and 0 for the other category. So let's call this entity the entity that they sniffed, and let's imagine that we code it with a 1 when the dog sniffed an alien and a 0 when they sniffed it as a human. So sniffing the human is kind of like our baseline condition. Now, our general linear model, we've seen this lots and lots of times before. We're going to predict vocalizations, and we're predicting it from which entity was sniffed. We've got a parameter representing the effective entity, and in this context, that's going to represent the difference in the mean number of vocalizations when a dog was sniffing an alien versus when they were sniffing a human. And we have an intercept, which is the number of vocalizations that the dogs made on average, basically when entity is 0. So in other words, when they were sniffing a human. Now, this is all well and good. This is how we would set things up. The trouble is, in a repeated measures design, the variable entity is manipulated using the same dogs. So it's the same dogs that sniff the alien as sniff the human. And that's going to create some kind of dependency between the scores across those conditions. So a given dog has a given tendency to vocalize, has a given sensitivity in their nose. So the number of vocalizations they make when they sniff an alien is likely to correlate to some degree to how many vocalizations they make when they sniff a human. So we've created dependency by using the same participants. And what this is going to do is it's going to mean that our residuals, the residuals from the model, are also going to contain that dependency. So the residual for a given, the residual when entity is alien is going to be somehow correlated with the residuals for when entity is human. There's going to be a dependency there. So what this means is that we violated one of the key assumptions of the general linear model, which is that it should have independent residuals. When we've used repeated measures, our residuals won't be independent. And if you think back to the lecture on bias in the general linear model, basically what we know from that is that if our residuals are not independent, the model is going to have various forms of bias in it. So one way around this is to think of the model instead as a multi-level model. So we think of the data as being hierarchically structured. Now, whereas in the previous lecture on multi-level models, we thought about hierarchical data structures in terms of kind of clinical context, so being treated within a particular clinic. But you can also think, it was mentioned in that lecture that you can also think of a hierarchy in terms of observations nested within individuals. So in this case, for example, if we take a dog, our first dog, Milton, he has 4 scores nested with him in the main study. So he has a vocalization for when he sniffed an alien, a mannequin, a shapeshifter, and a human. So he has 4 vocalizations. So those 4 scores are nested within Milton. Similarly, if we look at Woofy, he has 4 scores nested within him, and so on and so forth until Professor knows she has 4 scores nested within her as well. So it's a hierarchical data structure where at level 2 we've got the dog, and at level 1 we've got the scores that they contribute. Now, we saw last week that we can model this kind of situation with a multi-level model, and this is exactly what we can do when we have repeated measures. So our model takes on the same kind of generic form of the general linear model. So we're still predicting vocalizations, we're still predicting it from entity, we've still got a parameter representing the effective entity, we've still got a parameter representing the mean number of vocalizations in the baseline condition, or when entity is 0. We're representing them now with gammas because it's a multi-level model, but if you prefer to think of them as B's, then replace all the gammas in your mind with the letter B. So everything's kind of the same. We've got 2 subscripts now. We've got an I and a J, and these J's, the contexts, are the dogs. So J is representing the different dogs. So we've got scores nested within different dogs. So the first thing we can do is we can allow intercepts to be random. So to have a random coefficient for the intercept, which is in fact what we've done. That means there's going to be an overall kind of group level intercept, and there's going to be a term representing the variability in individual dogs around that group intercept. So this U term is telling us what the variability in intercepts across the different dogs is going to be, like whether that's big or small. By modeling that, we are modeling the repeated measures aspect of the design. So just by adding a random intercept, essentially it's kind of job done. We have incorporated the dependency in the scores. But we can also go a bit further. So sticking with our simple example where entity is just representing 2 groups, human versus alien, we could also add a random effect for that as well, or allow that to be a random effect where we've got our kind of overall effective entity, but we've also got a term representing the variance in that effect across the different dogs. So we can factor that into the model as well, but we don't have to, but we can. So just sticking again with our 2 category example where entity is just representing human versus alien, what we're saying here is we've got this overall group level effect that's represented by the kind of the grey line down the middle, and that effect is going to be the difference between the mean number of vocalizations when sniffing humans and entities. And so that term there is representing this difference here, basically. So the difference between the 2 means, and our fixed effect, our group level effect of the intercept, is representing the mean vocalizations in the baseline group, which is a group coded with 0. By making it a fully random effects model, what we're effectively doing is saying that the dogs, the effective entity on each dog can be different. So we've added 2 terms. This equation is the same as before, but we've added a term represents the variability in intercepts. So that's representing the fact that those intercepts vary from the overall intercept. So basically the dots for each dog vary around this group level intercept. So that U is representing the fact that there is variability in intercepts. So there's variability in the number of vocalizations across the dogs when they're sniffing a human. And the term representing the variability in the sort of effect that we're looking at, that's representing the fact that we've got this overall effect, the grey line down the middle, but that U is quantifying the fact that that slope can be different across the different dogs. So if you notice, if you look at the grey line that represents the overall group effect, you can see that some of these individual dog effects, so the lines for the individual dogs, are different slopes. So to give an example, this dog here, slope is very, very much steeper for that dog, that is in fact Lord Centicle. So Lord Centicle has a much bigger effect, so there's a much bigger difference between his vocalizations for humans and aliens than there is compared to the group level effect. So this random effect for entity is modeling the fact that there might be larger or smaller differences in the number of vocalizations between when they're sniffing at aliens and humans for individual dogs. So it's like the effect we're interested in is varying, or we're estimating how much it varies from dog to dog. Okay, now the problem is I've simplified everything to make life easier. So I said, well, imagine just for a minute that entity only represents two groups, just sniffing at aliens and humans. But that wasn't what we had. What we actually had in our experiment was the dog sniffed an alien, a human, a mannequin, and a shapeshifter. So in reality, for this particular design, we'd have to split entity into 3 dummy variables or contrast variables, depending on how we were going to code them. Let's just use dummy coding and remind ourselves of what that would look like. And let's assume that we pick Mannequin as our baseline, because the mannequin is made of plastic. It's not actually a living thing, so that might be a good baseline to have. What we're effectively doing in order to put this into a linear model is we're going to have to kind of recode those 4 conditions as 3 dummy variables. So the first dummy variable, which we might call alien versus mannequin, mannequin is coded as 0. It's actually coded as 0 across all of the dummy variables, which is what makes it the baseline. And when the dog sniffed an alien, we're giving it a code of 1. And when the score represents a dog sniffing a shapeshifter, a human, or a mannequin, it gets a 0. The second dummy variable, we use a 1 for the vocalization score when the dog sniffed a shapeshifter, and 0 for all the others. And when the dog sniffed a mannequin, sniffed a human, we're giving it a 1 on this third dummy variable and 0 for everything else. So we've got 3 dummy variables, one representing alien versus mannequin, shapeshift, another is shapeshifter versus mannequin, the third is human versus mannequin. Okay, so here's our data. We've got our 4 entities that each dog sniffed, and we've got our 8 dogs that are color coded here. And the horizontal lines represent the mean vocalizations within each of those categories. So here's our model, and what we're going to do is look at what happens as we kind of add random effects to it. So because we've got these 3 dummy variables, our model's expanded quite a lot. We've got 3 predictors now, and each predictor has a gamma attached to it. So for example, we've got our dummy variable alien versus mannequin. We've got a gamma attached to that, which represents the mean difference between, or the difference between the mean number of vocalizations when the alien was sniffed versus when the mannequin was sniffed. We've got a gamma 2, which represents the difference in means when a mannequin was sniffed versus when a shapeshifter was sniffed. And we've got gamma 3, which represents the difference in the number of vocalizations when a human was sniffed versus a mannequin. And that the reason it's got a cross next to it, that's actually supposed to still be an arrow, but those means are so close together that the arrow's just got compressed into sort of the 2 points. So there's basically kind of no difference there. But anyway, gamma 3 represents that difference. So we've got 3 parameters now because we've had to dummy code our categories. Now, because we've got a repeated measures design, the first thing to do is to allow intercepts to be random. So we can let our intercept be made up of the group level intercept. And remember, because we're using dummy coding, this is going to be the intercept when all, the value of the outcome when all predictors are 0, which is going to be the value of the outcome in the mannequin condition. So the group level intercept is this value represented by this line. And then this U is representing the fact that each dog's intercept varies around this line. So none of the dogs have an intercept that is exactly on the line. They all vary a bit around it. So by modeling that, we've modeled the fact that there's kind of dependency in our scores. Now, what if we want to add a random effect of the entity that was sniffed? How is that going to play out? And I just want to illustrate how very quickly you end up with lots and lots and lots of parameters in your model, and possibly too many parameters to actually estimate. So, okay, if we want to treat entity, the thing that was sniffed, as a random effect, then the first thing we need to do is add a random coefficient for the first dummy variable. So gamma 1 is going to now be made up of the group level effect, or the group level difference between the mannequin and alien groups, but also an effect U that estimates the variation in these slopes. So the fact it's going to model the fact that those slopes are different from dog to dog. It's okay, that's fine, isn't it? But we're also going to need to add a parameter representing the fact that the effect might be variable for the second dummy variable as well. So for gamma 2, we're now breaking that up into an overall effect or an overall difference between the mannequin and shapeshifter condition, but also a variance term, a term that corresponds to the fact that these slopes, the slopes between mannequin and shapeshifter, all vary or can vary from dog to dog as well. And you can see where this is heading pretty quickly, I'm sure. Of course, we then also have to add in a random coefficient for the final dummy variable of human versus mannequin, which is going to represent the fact that the slopes from mannequin to human are also variable by dog. By dog. So by introducing a kind of a random effect of this sort of one predictor, we've actually ended up having to add 3 variance terms. So from starting off having 4 parameters to estimate, the ones for the 3 dummy variables and the intercept, we've now added an extra 4 variance terms to that. So we've kind of doubled the number of parameters, but actually by default we'd end up with even more parameters than that, because we'll also estimate, or the model will by default estimate, the correlations between slopes and intercepts. So you basically end up very, very quickly with a very escalating set of parameters that you need to estimate. So that's something to bear in mind. It's not as straightforward as, oh, we just treat everything as a random effect and our model is gonna converge, because that, quite often doesn't happen. So it's it's a sort of you've got to think about what you're doing. I think that's the moral. So how does this compare with traditional approaches? So often in the past, people treat these kinds of designs with what's known as a repeated measures ANOVA, or an RM-ANOVA design. And what this does is it's basically a special case of what I've just been describing. And it's a special case that restricts the model in 2 ways. So first of all, it assumes effects are equivalent across participants. So it assumes that whatever effects you're interested in are fixed. So you can't have random effects, or typically you don't have random effects. That may or may not be a bad thing, but it also assumes that errors have something called compound symmetry or sphericity. Compound symmetry basically means the correlations between scores need to be the same, roughly, and sphericity means that the differences between pairs of scores have to have the same variance. And often these restrictions are unrealistic, or you might not want to have them. If this is approach for you, there is actually a version of this lecture also available, which it's got the same name, but it says affix after it. And that will do something more akin to this. So if you're finding this lecture hideously confusing, maybe have a go at the other one and see if it's less confusing. It might not be, because there is a common element to both lectures, which is me explaining everything. By using a multi-level model approach, we don't require compound symmetry or sphericity, so there's fewer restrictions. We can include more complex data structures should we need to. So we could have dogs nested within training clinics or whatever. In general, multi-level models cope well with missing data, whereas repeated measures ANOVA cannot. You need to have fully balanced design. And we can extend multi-level models to situations where we've got categorical outcomes. Can't do that with repeated measures ANOVA. And you can do things like contrast coding and stuff like that. But it's not the panacea to everything, because, like I said, the models get very complex very quickly, and you will find there are situations where they won't converge and stuff like that. So fitting the model, basically the trickier but more flexible option is to do a multi-level model, and you can do that. There's a package LME4 and another one nlme. In this lecture we use nlme, mainly, well actually it doesn't matter why, but that's mainly what we use. So you can set contrast with this, you can get the usual parameter estimates, diagnostic plots, all the things that you're used to seeing if you've been following these lectures. So let's have a think about contrasts for this first study. So if the dog training has been successful, we'd expect the sniffer dogs to make more vocalizations when sniffing alien entities than non-alien entities. So one, and there's no correct or incorrect contrast really, these are just the ones I've come up with. So the first contrast might be to compare kind of yeah, like I say, alien entities with non-alien entities. So we lump alien and shapeshifter together because you'd expect them to smell different to humans and mannequins, and you might put humans and mannequins together as the sort of control. So in both of these, in that contrast, we've got 2 chunks, and each chunk contains 2 groups. So we then have to further decompose the contrast into another 2 contrasts, one looking at alien versus shapeshifter, one looking at human versus mannequin. So basically we've got 3 contrasts, anything alien versus anything non-alien, and then we break apart the alien part to compare alien and shapeshifter, then we break apart the non-alien part to compare humans and mannequins. If you use the rules for contrast coding that we've covered in a previous lecture, you might code it something like in the table there. So contrast 1 that compares aliens against non-aliens, all the alien stuff gets a weight of 1/2, and all the non-alien stuff gets a weight of -1/2. Contrast 2, alien versus shapeshifter, we give human and mannequin 0 to get rid of them, and then the other 2 groups are 1/2 and 1/2. And we also code contrast 3 by giving alien and shapeshifter 0s to get rid of them, and we give 1/2 and 1/2 to, 1/2 and -1/2 to the other 2 groups. So how do we fit the model? Well, first of all, we set contrasts in the usual way. So the contrasts in the table I've just described, we would first of all set them to our variable entity. So entity has those contrasts attached to it. So I've labeled them sensibly, like alien versus none and alien versus shape and human versus mannequin. Then I've set the contrast for the variable entity. Then we basically build up 3 models using LME, so using the same function that we used for multi-level models before. So first of all, we predict vocalizations from the intercept, and to begin with, we just want to have a random effect of the intercept. So this kind of deals with the repeated measures and nature of the design. So that's our baseline. I've called it sniff random intercept. Then we add in our effective entity. So now the only thing that's changed is the highlighted yellow line, where we've got vocalizations predicted from entity rather than predicted from the intercept. And then we could, although we're not going to do this, but we could, if we had enough, if we had more than 8 cases of data, we could have a look at vocalizations predicted from entity, where we then allow entity to be variable over the participant, or the dog name is the variable. And then what we could do is compare those models in, again, in the way that we learned when we did multi-level models. So I'm just going to have a look at the overall effect by looking at sniff ent. So this was predicting vocalizations from the entity that was sniffed, but with a random intercept. And you can get a nice little ANOVA table like this, and we can see that there was a significant effect. So we can say the entity sniffed had a significant effect on the number of vocalizations by sniffer dogs, p equal to 0.01. So it looks like the dogs were able to discriminate overall between those 4 things, or the 4 things they sniffed. And then the contrasts are going to tell us where those differences lie. So having a look here, we set up the contrast. The first contrast we set up to compare when they sniff alien stuff versus non-alien stuff, and we get a significant effect there. So it looks like the dogs can discriminate between aliens and non-aliens, which is good news for us. We had another contrast trying to break apart whether they could discriminate aliens from shape-shifting aliens, so aliens that look like aliens versus aliens that look like humans. And that's just about non-significant. So it didn't quite cross the threshold, but if you look at the effects on those 2, they are kind of reasonably similar. And looking at could they discriminate a human from a mannequin, the answer is well and truly no, which is slightly odd because mannequins should smell of plastic and humans on balance should not smell of plastic. But the dogs did not make more vocalization. So, I mean, maybe that doesn't mean they can't discriminate them. Maybe it just means they're about as excited by a human as they are by a piece of plastic, whereas they're much more excited by aliens. I mean, actually, I guess if their training is to just discriminate aliens, it does make sense that, I'm just about to completely contradict what I just said, kind of does make sense that they don't make more vocalizations for humans and mannequins. Days, you're back. Good news. The sniffer dogs did well. I'm optimistic.
We have intercepted another transmission. It's more bad news, I'm afraid.
Oh no. Show me.
Lazing Dirt, mighty leader, I have returned.
Ah, Tunic Lane. How is the shape-shifting training going?
Exciting news! I can do the hands! Look! I've got human hands! But I'm having a bit of difficulty with the face now. I can't stop my face from being green!
Why are you here?
Ah, well, I have intercepted a report from the humanoids. Take a look.
Ah, the humans plan to use sniffer dogs to detect us, and their early research shows that they have succeeded. This is bad, very bad. But given our natural odor of putrefying bog water, this does not surprise me. However, we can make things harder for those disgustingly cute fluffy dogs by masking our smells with human pheromones and the scents of foxes.
Dogs love foxes.
Quick, Tunic, find me some humans and foxes that we might rub our bodies against them.
As you command, mighty leader.
I told you, not good news. They don't like dogs. What kind of evil creatures are we dealing with?
Masking their alien smells with scents. Interesting. But I'm not sure it's going to fool our sniffer dogs. Let's do some more research. So it looks like the aliens have ramped things up by trying to see if they can conceal their scents. So we need another study basically to look at this. So we're going to do a bigger study this time. We're going to have 50 sniffer dogs, all participating in all conditions. But now we're going to have them sniff 9 different things. So we're going to have one predictor, which is the entity that they sniff. We're going to get them to sniff humans, shape-shifting aliens, and non-shape-shifting aliens. But we're also going to manipulate the scent that each of those entities is wearing. So we'll have some of them wearing no masking scent at all, so they just smell how they normally smell. We'll have some smeared with human pheromones, and we'll have some smeared with fox pheromones, and we'll cross that all over. So, for every human that they sniff, one human will be, kind of as it comes out of the box. Another one will be smeared with more human pheromones, well, I guess from a different human. And one of the humans they sniff will be smeared with fox pheromones. Same with the shape-shifting alien, same with the non-shape-shifting alien. And again, as in the previous study, we'll just use the number of vocalizations during the 1 minute sniff that the dog does. So the model we're going to fit is now more complicated than before. And I'm going to, again, simplify things just in the interest of getting the equation on the screen by ignoring the fact that entity and scent mask will both be represented by 2 dummy variables each. So entity, they sniff 3 things, human, shape-shifting alien, alien, so that will be coded in 2 dummy variables. Scent mask, there's 3 types of scent, none, human, fox. That would also be coded as 2 dummy variables. So actually, in reality, you need to, where we've got entity, you need to, in your head, imagine that needs to be doubled up as a variable with an extra parameter. And here, where I've got scent, because I'm simplifying, you need to imagine that that's going to also be doubled up to 2 variables, and there'll be another parameter in the model. And if we look at the interaction between entity and scent, that will actually be broken up into 4 dummy variables, the 2 for entity and the 2 for scent multiplied. So we'd have this thing here is actually representing 4 dummy variables, each with its own parameter. So basically, this is like a hugely simplified version of how many parameters we're going to have. So if we made it a fully random effect model, we'd end up having a parameter for the intercept and the variability in the intercept, a parameter for entity and the variability in entity, and like I said, it would actually have 2 there. We'd have a parameter for scent and a parameter for the variability in scent. Again, that would actually be 2 because it'd be coded into 2 variables. and we'd have one for the interaction and the variability in the interaction, except, as I said before, there'd actually be 4 of them. So even though this looks quite hideous in the sense that we're estimating 8 parameters, in reality we'd actually be estimating, well, if you exclude the correlations between all these parameters, we'd actually be estimating, what, 2, 4, 8, 9 parameters, something like that. Sorry, 9 parameters representing random effects, so representing variability. So we may not want to do that. We may not have the data to do that. So the simplest model we can do to handle the fact that we have a repeated measures design is just to make the intercepts random, and that is what we're going to do. We're not going to allow any of the other effects to be random. So here's our data, and as you can see, it's pretty similar to before. Each dog, so this is a dog with the attractive ID code of 56F9P, and that dog contributed 9 vocalizations. So that dog is occupying 9 rows in the tibble, and each of those vocalizations is coded according to what was sniffed and what scent it was wearing. So the dog sniffed 3 aliens, 1 wearing fox scent, 1 wearing human scent, 1 wearing no scent, 3 shapeshifters, 1 wearing fox scent, 1 wearing human scent, 1 wearing no scent, and it sniffed 3 humans, 1 wearing fox scent, 1 wearing human scent, 1 wearing no scent. And I'll show you a bit further down the data just to show, there's lots of dogs, they all contribute 9 scores. This is what the data looks like. So face value, it looks like when no scent was used, there's like there's a huge difference here between the vocalizations made when sniffing alien stuff compared to sniffing human stuff. That difference kind of gets compressed a bit when they're wearing a human scent, and it kind of gets compressed quite a lot when they're wearing fox scent. Again, we need to think about contrasts for both the entity variable and also the scent variable. So the natural control group for entity is a human, because we've got human versus aliens. So we could just dummy code this, so we compare alien to human and shape-shifting alien to human. That seems a reasonable thing to do, so that's what we're going to do, standard dummy coding for that. And we also have a natural control for the scent masks as well, which is no scent. So again, dummy coding makes sense here. We just have the human scent versus no scent, the fox scent versus no scent. Have to remember these contrasts are not independent. We should technically correct our P's for multiple testing and all the rest of it, but these are sensible contrasts to do. So if we're going to specify these contrasts, it would be a good idea to start off by looking at which order our categories are in for each of these variables. So starting off, have a look, what order are the levels of entity? Well, it turns out they go human, shapeshifter, alien. So we want to use the first category as the baseline. And if we look at the variable scent mask, they go in order none, human, fox. So again, none is the first category. So actually we could use default dummy coding. We don't even have to set contrasts, and that's what it will do. But if we want to make absolutely sure that things are set up how we think they should be set up, we could use the cont treatment function, which is basically a function that sets contrasts automatically, so you don't have to worry about anything. And it does that by, you just specify how many levels there are. In both cases there's 3 levels, and you specify which of those levels you want to use as the baseline. And in both cases we're using the first level as the baseline, so we just set base equals 1, which I actually think might be the default of the function, so you might not need to even include that. So we set some contrasts, then we can build up the models like we did in the previous example. So we start off predicting vocalizations from the intercept. We allow that intercept to be random over the participants, over each dog. What changes in the next model? The random part of the model stays the same, that's not going to change, but we add in entity as a predictor. So scent ent is basically the model that has entity as a predictor in. Then scent is the model that has entity and scent mask. So we're taking the model above and we're adding scent mask to it. And then the final model, scent int, takes the model above, which has entity and scent mask, and it adds to it the interaction between entity and scent mask. So we're just building up a term at a time, and that is so we can look at the overall effects of each of each variable. So if we do a sort of summary of these models, we start off with scent base, so that's just predicting from the intercept. We add in entity, that significantly improves the fit of the model. We then add scent to the model, that significantly improves the fit of the model. and we then add the interaction term to the model, that also significantly improves the fit of the model. So basically by building it up like this, we can see what effect each variable has in turn. Knowing that we have a significant higher order interaction, we wouldn't really bother to interpret the main effects. There's no point because we know that those main effects are moderated by another variable. So here we're mainly going to focus on the interaction term. So the interaction effect suggests that the effect of entity on vocalization is moderated significantly by what scent the entity was wearing. And in a way you can see this relatively clearly from the graph, because when there was no scent being worn, like I said before, there's kind of a big kind of gap here. And as we look at different scents, that gap is narrowing. And so in all probability, this is what this moderation effect is. So the differences between the vocalizations to the three entities changes as a function of which scent they are wearing. However, we can break this down a bit more specifically by looking at the contrasts in the model. So this is the table of contrasts, and there's 4 contrasts that map onto the interaction term, and they're the ones I've highlighted in the table. They are all highly significant, and we are going to have a look at them each in turn. So over the next slides we'll look at this one first, and then we'll kind of go down and look at each one in turn. So refer back to this slide to see where they kind of fall in the table. So the first contrast, it's called Shapeshifter Scent Mask Human, which is helpful. So what this is telling us, remember that our baseline for entity was human. So the Shapeshifter tells us that this is Shapeshifter versus human. And then remember our control for scent mask was no scent. So the scent mask human tells us that this is human versus no scent. Now we can make this maybe hopefully a bit clearer by highlighting on the plot what we're looking at. So this is what this contrast is telling us. It's referring to this part of the plot. And the highly significant value is basically telling us that those two lines are non-parallel. Or another way to think about it is that this gap here is significantly different from this gap here. So it looks like when wearing a human scent, what seems to happen is that the number of vocalizations when sniffing a shapeshifter goes down somewhat, but when sniffing a human it goes up somewhat. So in other words, that kind of the gap between the vocalizations for human and shapeshifter narrows when the entity is wearing a human scent compared to when it's wearing no scent. So it kind of in a way suggests the scent is effective, but this isn't really helping the aliens very much because there's still this very substantial gap here. So although it has improved the situation, it's not going to stop our sniffer dogs from being able to sniff out a shapeshifter. So this is an example where a significant effect, kind of in the direction you're predicting, in the real world, if your alien invasion fleet starts smearing themselves in human scent thinking that this is going to help them, they would be wrong. So the second contrast, so the parameter for the second contrast, this is labeled entity alien. So that means for the variable entity, this is alien compared to the baseline, so alien compared to human. And for scent mask, it says human, so this is the human scent versus no scent. Again, let's have a look at what part of the graph we're looking at here. And we're looking at this part now. So again, it's a very similar kind of interpretation to the contrast before, which is that this significant effect is basically showing us that this gap is narrowing. So the difference between the vocalizations sniffing a human compared to sniffing an alien is much wider, or significantly wider, when they're not wearing a scent than when they're wearing human scent. But again, it doesn't help the aliens much because there's still this kind of enormous gap, even when they're wearing a human scent, that suggests that our sniffer dogs are still going to be pretty successful. Contrast 3. So this is entity shapeshifter. So this is shapeshifter versus human, and scent mask fox. So this is fox scent versus no scent. Again, let's see which parts of the graph we're looking at. We're looking at these parts. So, ignore everything else apart from these two lines. And again, the significant effect is telling us that these lines are not parallel, basically. And again, we can see that it sort of suggests that this big difference in vocalizations when sniffing a shapeshifter compared to a human that you get when there's no scent being worn is narrowed dramatically when they're wearing fox scent. But again, this doesn't help the aliens, because if you look at what's happening there, although the vocalizations to the shapeshifters do reduce, so that red line is going down, the more dramatic effect is when they're sniffing humans. So when a human is wearing fox scent, it stops the dog thinking that it's a human. But that doesn't help the aliens. So it only helps the aliens if the aliens come down and smear all the humans in fox poo. It doesn't help them if they smear themselves. So what is the effect of the fox scent is basically it stops the dogs noticing that it's a human. It doesn't particularly stop them from noticing it's an alien. So this will only work. Basically, the aliens need to dump a load of fox stink on the world, and then that might help them. Finally, we have this contrast comparing alien against human with fox scent against no scent. Let's have a look at what bits of the graph we're referring to. So that's these two bits. And again, the pattern is very, very similar to for the previous contrast. It's just suggesting that this gap here, so between the number of vocalizations that a dog makes when it's sniffing an alien versus a human, is narrowed when the alien and human are smeared in fox stank. Again, you can see though, although it's having a slightly more dramatic effect than it did for the shapeshifter in terms of reducing the vocalizations when they sniff an alien, when a dog sniffs an alien smeared in fox, but it's also having a kind of a dramatic effect on their ability to, I mean, they're basically getting more excited by sniffing a human when a human is smeared in fox. So again, it doesn't really help the aliens unless the aliens smear us in fox rather than themselves. There's still kind of a gap between the vocalizations for humans smeared in foxes and aliens smeared in foxes. So in a nutshell, good news!
Lazzing dirt! Bad news! Bad news! Our invasion has been detected!
How is that possible? The p-value was greater than 0.05 and we smeared ourselves with human sweat and fox poo.
Apparently, the effect size was large. The sniffer dogs were better at detecting us than we realised. And the scents, they didn't work. And the dogs were so cute that we wanted to cuddle them and live in harmony with the puppies and the humans.
Cute? Cute? But puppies are hairy and tonguey and licky and disgusting.
Oh, but they're so nice to cuddle. Why don't you try one?
Yes, I like its ears. Perhaps we should try to assimilate rather than invade. But how can we? As a species, we are socially awkward, aloof, uncool, logically minded hermits. We cannot exist undetected in the humanoid world. They are so sociable.
Well, I think there might be a way. The humans have a shortage of people that have all of our qualities. They're aloof, socially awkward, hermit-like, logically minded. They're called statistics lecturers.